So, please welcome Shuva Jyoti Kar with a big round of applause, who will be speaking on architecturing autonomous systems and cloud native technology.
Myself, Shuva Jyoti Kar, and as ENC already told my previous engagement, so currently I'm leading the agent security for next generation firewalls at Palo Alto as a senior principal engineer. And my area of focus is basically architecting autonomous systems in cloud native environments. So enough about me. Let's get started. So the safe harbor. So the opinions that have been expressed here are my own. My personal capacity and do not represent the views of the views, policies, or the positions of any of my employers or their subsidiaries. And all these names, characters, and incidents that I speak of here are a pure work of fiction. So for getting ahead, so what we will start with the agenda. So we'll first try and understand as to what is the difference between automation and agency. So automation versus agency. Why agents? So we have been talking about agents, there is RAG. So why agents in the first place? Then we'll look about what are the agent frameworks that we have currently. The agent runtimes. So from the frameworks, the runtimes, and then agent security. There's a small demo at the end. If time permits, we will get that. So automation and agency. What is automation and what is agency? So imagine automation. So every one of you, I presume, are engineers here. So we have Jenkins pipelines or automated CI processes that are in place. And so how does that differ from something like having an agent there? So an automation is basically, or you can imagine an automation as a train on tracks. So if the track is fine, the train runs at full speed. But if the track breaks down, you'll have to figure out what went wrong. So that's where your automation breaks. So it's a deterministic step-by-step process of getting things done. But in case there's a failure, you will have to do specific failure handling, or you'll have to engage somebody to try adjust to what they realize. So if you look at this flow of events, so it starts from a trigger event. So you check in the code, that's a trigger for you. You fetch the data, you get all possible things that are there, the Jira details, the PR details, the feature details and everything, figure out whether it's the correct thing for it. You format the data. In case there's an error, system fails, somebody has to get plugged in here and figure out what went wrong. In case there's a success, okay, so you update the database, the build is going on fine, the artifacts are already there, and you send the notification so that your manager, you yourself get notification is fine, and you end. So that's automation. So that's a train running on a fixed track. The track doesn't change, and in case there's an error, you have to manually, or somebody has to get in there and figure out what went wrong. So there is no feedback and no intelligence that's built into the system. So that's automation. Now you get into agency. So how do you basically figure out what an agency is? So it's definitely non-linear. So if you imagine a human reasoning system, so you have to get from point A to point B. So from Whitefield, I was driving in the morning, 20 minutes. So I figured out, okay, the signal has gone down here. There's a long traffic queue, so I'll have to pivot. So that's the intelligence that we are talking about. So it's non-linear, it's highly probabilistic. So it's goal-driven. So I know I have to go to Niemann's, but I'm not sure of the route. The route will be dynamic. So if you look at maps, that's the dynamic rerouting that it does. So there's a bit of probabilistic thing inside it. I have the destination fixed, but the route to the destination is probabilistic.
It self-corrects, okay? There's a blockage, I go back and I recalibrate. So there's a self-correction and an iteration loop in it. So that basically mimics how a human brain or a human reasoning works. So that's the agency. Now, I did 1 year of MBBS. Most of my terminology will basically revolve around medical. So what is basically the anatomy of an agent? What does an agent comprise of? So an agent comprises of the brain. So that's the LLM, the part that's here. It can be Gemini, Llama, it can be anything. So it's the one that's responsible for the thinking part of things. So there's a nervous system, the one that orchestrates the entire thing of action. So that's the framework. We have a memory that could be basically a short-term memory, a long-term memory. It can be a scratch pad. It can be anything. So based on whatever you decide, or how do you decide to share the state, it can be anything. So that's the memory part of things. Then there are tools. So tools you can basically think of as your limbs, your hands, legs, or something, or your side. So somewhere from where you will do an action. So it would be via an MCP, the Model Context Protocol for sure, It can be APIs directly, depending on how you integrate with the enterprise things, and it has an aura to it. So that's the persona. So you can tell it what's the tone, the guardrails that you need to figure out, the instructions. So these 4 components basically typically make an agent. So you have the brain, you have the memory, you have the tools, and a persona. Now the physiology. So how does an agent work? So normally if you look up Google, you would see a term called as React. So what does React mean? So it's reasoning and action. So just as I mentioned a slide before, the human reasoning part. Okay, so I do this. This is the outcome. I observe the outcome. Is this what I need? Yes. Go ahead. If not, recalibrate, pivot, and then go back and solve it. So it's a feedback loop. So if you look at here, so the React agent loop, it's a thought. You take an action. You observe. See what the outcome is. Goal is achieved. Well and good. Not, go back and do it. So that's the feedback loop for the React. So that's how an agent behaves. So that's the physiology of an agent. Now typical anatomical differences between an agent and an automation, the things that you need to focus on are the state management. So in automation, the state is transient. You don't carry the state of a previous failed build to the next run. It's transient and it dies along with the process. But for agents, it's pretty state heavy. You might break down a task into a series of steps, and for each of the steps, the state that you maintain might require in the next step as well. So you need something called as a conversational or a long-term or a short-term memory that way. And the scope of work, it's definitely different between an automation and an agency, and the infrastructure need is short-lived. It comes up, it dies, but here it can have a long-running compute, and that's where the part of our story starts. How do you architect something that has to have a long-running compute, but as Lawrence said, we need to reduce the costs. Let's see. So next thing, why agents? Why agents? So there's a beautiful story about it. So most of you might know about it, but I'll just repeat. So in the 1950s, Pontiac and GM had a customer calling in as a problem, saying that whenever I drive down a store to buy vanilla ice cream, my car doesn't start. But the moment I take something like a chocolate or a strawberry, it starts. So imagine that these data points are being fed into a system. Now the system is a RAG. So you can figure out as to how many times the car started. You can figure out how many times the car did not start. You can plot a trend line out of it. So you can do a whole bunch of retrieves. You can retrieve it within timelines. You can plot charts with it. But why? Why is something that a RAG will not be able to tell you? RAG will only be able to tell you what. So that why part of the things is where your agents kick in. You can do multiple rounds of retrieval, but correlating the retrieved data to something that actually works or something that can be reasoned about is something where your RAG basically fails. So that's where we say that a static RAG is not a go. So this is the human reasoning we have talked about. So now let's look at the agent frameworks. We'll take a bit, we'll compare ADK, Anyten, and we'll compare LangGraph and see how does a framework work. So a framework, as I mentioned before, is the nervous system for an agent. It basically ensures that it's an agent orchestrator. You can think of it as that way. So it given a user query, it plans, okay, these are the set of steps that I need to execute. It coordinates with the LLM, ensures that the LLM has the right question. The LLM is the one that maintains or retrieves the context, works on it, does an action, observes it, and then based on what the observation is, it proceeds or it loops back. So the one at the top, the agent orchestrator, is the framework. Now the key framework concepts would be, again, it's a repeat. So the brain, the nervous system, the tools, and how do you compare? So if you look at ADK is typically code centric. Yeah, I'm not at the edge. So ADK is typically code centric, like LangGraph, but it's skill based. So the logic model is quite different as compared to LangGraph. I always figure it out extremely difficult to code in LangGraph, but ADK gives me that much amount of flexibility. It's highly useful for cloud native. So based on any serverless platforms that you are looking at, ADK would be my first choice of coding. It's highly lightweight, and the control is pretty fine grained. But if you look at LangGraph, Anyten, or Diffie, the cloud native fit is pretty heavier here in these two parts, the Diffie and the innate in. LangGraph, it's easy, but the Python logic that's required is quite difficult for somebody starting off with. Again, flow into how the agent framework works. So you would have an user that interacts with an AI agent. The user queries, there's a stream response, and this is the agent runtime. So the runtime basically decides which model to use. It coordinates that, how to use the memory. So you would have Redis, you would have a key store or a val key, a vector store for any of your quadrant, chroma, anything, and your tools for connecting to the outside world. Now agent runtimes. Now, so after that, so we have the concept of an agent. We have the concept, we have mapped that agent into an agent framework, we have coded that. Now how do I deploy it? How do I deploy it? So there would be two you can deploy it in on-prem or you can deploy it in serverless. That's a typical framework for the cloud native environment. So why serverless? Now we were looking into this problem earlier in the morning when Lauren was speaking about. So the idle intelligence problem, the cost of waiting. So a typical AI load is burst in nature. It will come, it will be processed, and the maximum amount of time it spends is waiting for the LLM to give you a response. But do you want to pay that GPU cost while your system is still idling? That's the question, because you would have to pay, as he mentioned, $12 an hour. Now that's a huge payment if you're considering that. I'm just idling it out. So the cost of waiting and the scale to zero. So in places where my load isn't there, my agent is just idling down. Can I scale my agent to zero? So those are the two typical questions that we'll be looking at, and we'll look at a framework that helps us to achieve, that helps us to minimize the cost of waiting and helps us to scale down to zero. The next thing is event-driven reasoning. Now, your AI agent cannot keep polling for an input for the entire amount of the time it is live. So it has to be event driven, meaning based on a trigger for an event or a reaction, it will act, it will perform certain things, and it will go back to sleep. So that's the reactive scaling that we are looking about. And how do we do that? So there are two ways of doing that. It's either a KPA, native pod autoscaler, or a KEDA. We'll look into that as well. Ephemeral state, yeah. So for since I'm coming from a cybersecurity background, so you need to store state as minimal as possible, because the more state you store, you will have to ensure that it is sandboxed to ensure correct security. So you need to be ephemeral. So you just boot up, you process, and you die without leaving behind a trace for anybody to hack into the system or figure it out. So clean slate and decoupled state. Concurrency management, we'll look at how. So now, what are the options that we have for a serverless deployment of an agent? So we are looking at Kubernetes because, well, Kubernetes is everywhere, and it's the first thing that comes to any platform engineer's mind while you are trying to deploy it in cloud. Now, why does Kubernetes doesn't work in this scenario? Kubernetes is declarative, excellent, but it's static. What do you mean by static? So when a pod comes up, you allocate some resources and it processes traffic and it goes on. So you have some resources that are tied to it and it's processing, but imagine that the traffic dies down. So I don't have any events, I don't have any workload for the agent. It's bursty traffic. My pod still runs. And what do you mean? What do I mean when my pod still runs? It's still billing me. And when I'm looking at like enterprise deployment, it's close to thousands of dollars per hour. We don't print money, but this is one of the most important places wherein within this year we'll be looking at optimizing costs. So if 2024, 2025 was early adoption of AI, 2026 would definitely be the year where we'll be looking at optimizing the cost. So yeah, it does not natively understand request concurrency. So Kubernetes basically does it auto scales based on CPU and memory, but agentic load is something different. So it's L7 routing that it has to understand, but unfortunately Kubernetes doesn't do that, and it cannot scale down to zero. So that's where Knative comes in the picture. Now, what is Knative? It's a platform for managing modern serverless workloads. How does it do that? So there are two control planes: the Knative serving and the Knative event framework, eventing. The serving is basically a request driven compute, meaning it's based on the HTTP load, the number of concurrent sessions that are established to it, it will scale out. Eventing, it's again an event driven architecture. So based on the amount of events that are incoming, we convert that into cloud events, and then based on the cloud events, we have a typical source sync broker methodology by means of which we control this scale. We'll figure it out. So there are two parts to it, two parts to the control plane. One is serving, one is eventing. Now diving deep into that, the Knative serving, it has 4 custom resource definitions. So the configuration is basically the declaration of deployment. Your environment variables, your images, so those whatever you write, your application logic, so that basically forms the part of the configuration. The next thing is revision. So if you take a static snapshot or an idempotent snapshot of the configuration, that's your revision. Now you change anything in the environment variable. Okay, my Docker image changed, my passwords changed, my cloud provider changed, unfortunately. So that's a different revision. So you have configuration, you have revisions of that configuration, you have routes. So route would typically be the networking configuration or the networking layer that maps this revision to a URL, because the URL is something that we all will access. So you have a configuration, the configuration changes, you have revision, you can have multiple revisions, but you can have one or multiple URL endpoints specific to a revision. So that's your route. Service is something that encompasses everything. So that's the topmost layer. So now how do you basically scale to 0, and how do you basically do a warm reboot? So we will have two heroes in here. One is the activator and the autoscaler, and we'll see how. Okay, so the magic of zero traffic loss. Imagine that you are sleeping. You are sleeping in class. Okay, going back, a story again. So you're sleeping in class, and the teacher asks you a story, asks you a question. Your prof is asking a question, you need to answer. Keeping that picture in mind is what an activator and an autoscaler does. So when an agent is scaled down to 0, there are no pods which are running. So a request comes in. A request, when it comes in, it will come to the ingress gateway. It can be either Istio or it can be either an Istio or an envoy. You take that, and then it computes the route. Now the route basically has a component called as an activator. Now the activator is intelligent enough. It knows that there are no pods which are running. Because there are no pods which are running, I'll do an interesting thing. And it somehow borrows the concept of handoff from Dynamo. So what does it do? It buffers. It buffers the HTTP request till the point this is interesting. So if we are looking at cybersecurity part of things again, so I have millions of logs coming in, and I need to figure out whether an IP is rogue or not. So I have events coming in. Now for each of those events coming in, we'll wrap it into a cloud event. That's basically a CNC construct again, and we put it into a source. So that's we identified as a source. The source could be a firewall, it could be webhooks, anything. And we take those events and put it into an event bus or a broker or an event mesh for that matter. We have triggers or filters that are put on it. So if I say that it's a is it coming from an open encrypted endpoint? So yes, open encrypted endpoint, these are the things that are coming in. So that triggers. So the filter is kicked in, and we have a routine that goes to the sink. So the sink is, imagine the sink as a Python code or a tool that gets triggered when we have filters that are coming in, or when we have the triggers getting triggered. Now from the sink. So the sink is a piece of a process that runs once we have a trigger. Now the sink will not be in memory, so it's not a memory process. It doesn't run in the memory of the agent. The job of the sink is to ensure that it will create a sandboxed environment which is ephemeral, number one, and which is cut off from the outside world. It will run the process, take the output, and it will die. Two reasons because of that. Two reasons for that, because we all understand the vulnerabilities of a typical LLM with respect to prompt injection or with respect to getting a system down. So if I'm allowing an agent to run a tool in the memory of itself, the probability of it going down becomes higher. So what it does, it spins up an ephemeral pod, it runs within that, it ensures that it's a virtual private cloud, it's locked down from the outside, it doesn't have an egress, it just runs, gives the output back, and it dies. We'll see a bit about that into this. And so again, a magic, abracadabra, it scales down to 0. How does it scale down to 0? So when the autoscaler figures out that there are no active input traffic and the activator memory is 0, it just scales down. So whenever somebody tells you that, okay, we have a cloud native solution that scales down to 0 when there is no traffic, that's what actually is happening behind it. So why Knative wins for agents? Three things: concurrency. It's able to allow multiple concurrent connections per container. The containers will be created based on the input load. It can scale down to 0, and it supports 0 traffic loss. Again, extended execution, it can run up till 60 minutes with respect to the request timeout. So that's something that's in depth for Knative. So this is basically split up because of the screen space. So if you can see the event sources, it can be from anything. So the event sources, I've taken a Kafka stream, so it's wrapped into a cloud event, sent into a broker, it triggers. The triggers basically go inside an H2 ingress, so that's basically your gateway from where the activator picks up. In case we have the pod running, that's one path. In case it doesn't, it wakes up the autoscaler, it handles it, and then it does what it does best. So the agent security, given that that's one more part of things that we normally tend to retrofit into the architecture, I thought of bringing it up. The risk is you do not give agent the keys to an LLM. We have seen deployments, or we have seen customers wherein the agents had keys to the LLMs and things have gone bad, so bad that we cannot even mention that. So we do not give keys of an LLM to an agent itself. Now how do we do that then? So there is a concept of a AAA, authentication, authorization, and an accounting, and there is a concept of service accounts. So each of these agents to use a protocol that abstracts the tools to an extent that they can be called from a sandbox. That's where the MCP comes in. So we decouple the agent's brain from the tools that it uses. It's standardized and it runs in a sandbox. The VPC control, yes, we mentioned earlier, we need to lock down the Knative environment for doing it. So now the demo, I think I'll have 5 minutes of time. So we will be looking into architecting a cloud native security agent swarm. So imagine that again, you are triaging a cyber security environment wherein you are bringing in a lot of events. A single agent cannot work, and you will have to spin up multiple agents. So how do you basically scale that up, and how do you basically build a platform that can handle that? So it's an I'll do it step by step. So you have an API gateway that gives you the ingress traffic. You have an agent framework, the reasoning code that runs in a agent runtime, and it stores the state in a memory, CHDB or a ClickHouse, for example. And so now the next step is building in security. So I get the MCP server as a sidecar, so that abstracts out the external APIs So I decouple the tool execution from it and store the state outside. I get Knative in, so your activator and the autoscaler to ensure that it scales up when it's required and it scales down to 0 when it's not. This is the entire thing in picture. So tying it all together, the async trigger, the concurrency sweet spot, because you can run multiple requests in parallel, the stateful memory, because my agent pod doesn't store the state, I store the state outside. So it's a stateful memory in a stateless pod, and the security boundaries of the sidecar. So we go from, so this is the most important thing to understand, is that we go from a sequential bottleneck. So imagine that you have 50,000, that's a very small estimation, 50,000 events per second coming in from a security pipeline perspective. Your solo agent pod can give you a latency of roughly around 1 to 2 seconds. So that's unacceptable in any security processing pipelines. Now imagine that I'll have to scale this up. So how do I scale this up? So I put this in Knative, or we put this in a platform, cloud native platform that's designed something similar to Knative. So you have an efficient routing that takes place. The pods scale out based on the input load. That's again your autoscaler in action, and you process it with roughly around a few milliseconds. So this comes down to roughly around how much did I mention? It's roughly around 30 milliseconds. In case you have questions, you can feel free to ask now. So this QR code basically gives you an article. So I write on Medium, multiple articles on Medium with respect to cloud native environments and technicals around AI and architecting AI systems. So this is a QR code for the specific article that is behind the presentation. Feel free to scan that.